I heard you say about Aeroplanes.
No, we're just like that.
Yeah, I get it.
Yeah.
How come I know if this is working?
She's like, do you want?
Think about the book of it. Wet, down, not
Can you help me with the AV guru? How the problem is that I might explain that. My screen box.
So, what am I going to say? Is it just a? Then I join out.
Yeah, quite maybe that's why good idea.
Testing.
Okay, cool. So that should be.
Okay.
Yeah, that's too weird.
So yeah.
The whiteboard instruction.
A little bit, yeah.
No.
Wait, how far forward can I sit without
Strike's fine.
Where does the view start?
Sorry?
Increase the font size a bit.
Well, we'll just zoom in. Where's the-
Fine.
Are we ready for the talk?
Yes. I think so. But what I'm also going to do. So that's the microphone.
Okay, that's the microphone.
But I will also record on my phone.
Good. Don't want to miss any details.
Exactly. Douglas. You know, we could probably bring this forward.
That's a good idea.
Not anymore than that. All right.
Cool. All right, so this is my talk about the Ethos 2 netcode. I wrote most of it in August 2009. A lot of other people worked on it as well, obviously. It was mostly unchanged for Ethos 3 and G-Star. It's quite complicated. It's actually been iterated on, and a lot of ideas are in the generic netcode. Obviously, I prepared this weeks in advance when the documentation wasn't ready. But there's that was a joke. There's some good documentation of the generic netcode here, which is good too. But I'm just mostly going to talk about what I know about. So what we're trying to learn. Oh, it doesn't even line right. Sorry. So we're going to get a high-level understanding of the problem domain, constraints we're working under, and what we're trying to optimize towards. We're going to get some understanding of how the Ethos 2 netcode and Ethos 3 netcode work, and we're going to get some fire at the cool tech, and we're going to get some passion. It's going to be good. I haven't been too careful about everything I say is just my own opinion, obviously. I don't think most of it's very controversial, but not sure if I can words in anyone's mouth. So in Ether, we've got in a game written in Ether, simulating many entities, also known as agents. I mean exactly the same thing. players of the game need to be able to see what's going on through their client. The ether simulation progresses in ticks. So 20 hertz, you've got 50 milliseconds for a tick. Every tick, the ether workers compute the evolution of the simulation. And we're really interested in how the clients get the information that they need to display that to the user. So what are the clients trying to do? They need to be accurate, reliable, cheap, and prompt. I can't think of any other categories. And obviously these things are in conflict with each other. Cheap means we need to send as little data as possible. And also it means that the compute that we require of the various components can't be ridiculous either. Got lots of different types of clients. OpenGL client, or as I'm trying to rename it, the debug client. The auto client, which I like to call killer robot. Gateway auto client. This is a cool one that's new, that gets a bunch of information from the headers in the packet so that it can integrate with PlayFab and not let too many players in at the same time. So the gateway auto client knows how many players are in the simulation, and so it can drip feed them in. Game client, very important, usually Unreal Engine at the moment. And admin client doesn't exist, but this is something that we're going to need, where the client can, it's a client that can talk to the simulation and control it. So maybe you want to kill your friend or whatever. mooxer. All right, it's going to get more interesting. So we've got a mooxer component, it's a Linux server program, and we all wish that it was a Helios program. By the end of March, we're going to have a mooxer ready operating system, at which point we'll be able to put the mooxer in Helios. So something to keep in mind is we need to make sure that the strategies we use are going to be amenable to that coming transition. And the workers send the state of every entity to the mooxer every tick. This is okay for the minute. It's not great, but it's okay because they're all in data centers. So you've got a lot of wiggle room for bandwidth. But what you could do is you could just send it once to every data center and then fan out to all the mooxers in the data center. This would save you some money on peering.
There is code in Git to do this.
Is it?
Yes, just nobody's ever used it or.
Really? We should use it. Then now we're going to later on talk about some tricks for how to send this data, and we could utilize these same tricks when we're sending data from the workers to the mooxer, because it's the same kind of data we're talking about. There's a lot of the problems are very similar. Handover is another part of Ether that involves sending details about entities to other people and or other programs, and that probably also utilize some of these tricks, in my opinion. So if we could do whatever we want, we just send everything every tick, but we don't live there, and that's why Ether is useful. For the same reason that Ether can't simulate the whole thing on one machine, eventually, the client cannot process the whole simulation on the client. So we need to find some way to split the work up and only send the client what it needs. Right. So history. So we created the mooxer. It was originally, I believe, 100 lines of Rust by Aidan. And it just forwarded the work. So the worker sends a state packet to the mooxer, and the mooxer sends that to every client in the most naive way, and it eventually didn't work. We then had net relevancy, which was implemented just as I joined. So this exploits the fact that the workers have spatial information about them, so we just send important worker packets to clients more often.
There was a midpoint. There was a midpoint between this. Yeah.
Was it?
Yeah.
Okay. I guess it didn't really work out though.
No, basically it was the mooxer being packet aware, but not doing net relevancy. So we're trying to synchronize the whole state of the simulation, but not with any level of net relevancy. So it
Oh,
didn't,
okay.
didn't know about players, but it could sort of avoid sending packets to avoid sending the whole state.
Oh, okay. All right, and I hear that this was about 1.3 megabytes a second, although I've heard other numbers that were higher, which makes the rest of it more impressive. Poor gameplay experience and lots of dead torpedoes, which are they're awful. If you've ever played Ether Wars 1, you will know what a dead torpedo is.
Space is really empty. Like, it's really dull. That's why you need these torpedoes there that you can't interact with.
Yeah, I mean, if they were not stationary, I wouldn't have so much of a problem with it. But it's not what things do. In space, they keep moving. You know,
Yeah, unless they have no velocity.
torpedoes always have velocity. Anyway, so dead torpedo problem is that entity in a simulation dies. It's a dead flag set on it. This is supposed to go out to the client. When packets get dropped and the client doesn't see that dead message, there's no way for it to recover from the situation. It just it heard about a torpedo and then it never got another update again. So what's it supposed to do? Because it's normal for it to not hear about things for a little while. And what ended up happening is you ended up making these clouds of torpedoes. And that was really, for me, the defining feature of Ether Wars 1. Ether Wars 2. So we needed to send much less data and we needed a better gameplay experience. Wrapping lines. And we need a solution to dead torpedoes. So we decided that the mooxer needs to look inside the packets to understand more about what's going on so that it's able to make decisions. And essentially, every tick for every entity client pair, it needs to decide whether to send that entity to that client. Now, naively, this doesn't work because if you want to have 100,000 entities and you want to have 2,000 clients, then this is 2 million. Is it 2 million? No, it's like 200 million. It's 200 million entity client pairs. It's very quickly going to become untenable. So you have to make, there has to be some give, which we'll get to. What ends up happening is we don't send every entity to every client. We just talk about, we just send entities that are close to a client to that client. But importantly, the mooxer needs game-specific code. Before this point, nothing has been game-specific. These workers have just been sending opaque blobs of data, which are then sent to the clients, and none of this depends on what's inside the data. So yeah, the mooxer is going to need game-specific code. So it's refactored to expose a C API. Net relevancy consumes that API and does the same thing. Still some controversy around the details of that API. mooxer.cc is written, which exposes this approximate interface. So you need to be able to deal with getting a new packet from a worker at a time. This is the data inside the packet. And you need to be able to generate a packet to send to a client. So this is coming from the worker, and this is going to the client. This has been edited for pedagogical reasons. Is that how you pronounce it? So new packet is called when a packet arrives, build packet when it's ready to receive data. So the idea is that Ether game, so inside the Ether simulation, there will be, is that what I'm saying? So yeah, the user inside the simulation serializes into the packet in an arbitrary way, and then deserializes it through the new packet function into some game-specific representation. And then when build packet comes, then we query this game-specific representation and then serialize some arbitrary way, and then the client deserializes that again in a game-specific way. So I'm going to actually draw a diagram of this because I think it's quite important. So you have, this is the simulation here, and then this is the mooxer, and then this is the client. So then this is ether, and then this is the simulation. So this part is written by the user, and then mooxer, again, this is our proprietary code, and then this is the net code. So what we can think of happening is it goes like this. And the simulation that the user writes talks to the net code that the user writes, which then here talks to the client. Again, the user writes. We have very little here, but the same tools, in my view, it makes sense to use the same tools to talk about this data here, here, and here, so that these things are going to be necessarily very tightly coupled together, because they need to understand what each other are thinking, so that they can not send information that the other one is already thinking. So we send entities that are far away, we send them this frequently. Some entities we don't send very often, such as resource nodes, because they don't move, they don't change very much. Don't send fields that haven't changed. So, for example, the type of a torpedo is always going to be a torpedo, so you only have to send that the first time. Now, in honesty, we haven't implemented all of this. In particular, this one hasn't been implemented. The infrastructure for doing so is there, but it's not done. We have also, this is implemented, but it's not used very much. The main thing we do is we only send things that are close. And we send them more often. And the reason that it's the case is that this part here, you interpret what you get. Our failing here is not having the tools here that we needed. Because I'll get to it later, but we needed to have something here that was able to reconstitute something that the user can work with, essentially. Okay, so how do we accomplish this? We keep a global database of the state of the world in a world DB. It gets updated on a new packet, and we keep a per client database, something in the client called a player DB. So when build packet is called, we end up in build packet symbol, which is Aiden's favorite function. So we return early if we've got nothing to send. Otherwise, this is another good opportunity for a picture. Just someone in. You just do it. Oh. Owner's left. Oh, nice. So, if this is the player that we're talking about, then we do a query for things that are close. We see all the ships that are close, and we don't see squares. And then for everything that's close, we try and add it into the player DB. And if it's not already in the player DB, then it gets scheduled. Then the next step is to ask the player DB for entities that are scheduled to be updated again this tick. We put them into the packet and decide when to schedule them again. I'll go into that a little bit more detail later. So we can't send every entity. We can't send every entity to every client. It doesn't work. We can't do it. So we only send close entities to clients, and we need to. If the more entities we want to send, the less often on average we have to send them. World DB. So this is a data structure with 3 jobs. It needs to be able to update the state of the world. It needs to be able to answer queries of give me everything in a sphere, that's what that is over there. And it needs to be able to answer queries, give me a specific entity. So we have a hash table of workers, and each worker has a deck, and each deck is where these entities live inside the WB. It's not good. I think it works differently in the generic net code. I'm not exactly up to speed, but yeah. So this problem here, which I'll again draw a diagram of.
Yeah, the generic net code just has one single store.
Yeah, it's a better way to do it. So you've got two workers, and you've got a person there, and then person goes there, and then you get this update before it happened, and then you get this update after it happened, and suddenly the guy's gone. So, like, we do compensate for that in other places, but it's just not something we should have to deal with. The reason that it's done in this way is to try and give better data locality. Because the idea is that this way you're storing you're storing the entities that are close together next to each other. But I think that the new one that Francis wrote has this property as well.
Not
Squinting.
slightly less, perhaps, but it has other good properties. Can't say.
Yeah. We use boost intrusive to hash index them to satisfy the third property. I'm really biased here. I think boost intrusive is really cool. So I think this is a really good idea, but I wouldn't trust myself. It's quite fiddly. It's easy to get segmentation faults, but it's quite fast. We also maintain separately an R tree, which is a spatial index, and that enables us to run these queries. It's a bit of a nightmare. It works well, except that it's slow. And so we've got all kinds of nasty tricks to make it tolerably fast. If we used a different spatial indexing structure, we might have a much better structure. Everyone keeps telling me that NanoPlan has worked really well for them, so I think we should probably try NanoPlan. Yeah, so we have a dedicated thread to update the R tree. It's got a trippy algorithm that I've expressed in one paragraph. And I'll draw a picture of it as well. So we have a queue, and when the packets come in, they get thrown on the queue, and then there's a dedicated thread for the R tree that will take the queue. I'm going to draw this. It's got an R tree here, which I'm going to draw as an off tree. And so it locks this, puts all this stuff in, and then if this is in swaps these two R trees. I'm both blocking it and going to draw. So the idea is that you have two and you swap them. So the threads that are servicing clients are able to query this R tree while the updating thread is updating this R tree, and then you swap them. And then of course the updates that you've just applied here aren't here, so you have to apply those updates first and then the new updates. So every time you're doing it, you're applying the previous queues of updates followed by this queue of updates, and then swapping. Does anyone understand that?
Double buffered the world.
Yeah, you double buffer the world essentially. One person put their hand up this morning. All right, so what's wrong with this? If you have a queue, what ends up happening is you've got like t minus 100 in practice, and then you've got like t minus 50, and then you've got the newest ones here. But these things don't really matter because they're in the past. This is the same idea of UDP of when you're streaming, that only the new updates really matter. So what we should be doing here is just storing one packet per worker. And then if a new packet comes in and we haven't processed it yet, then we should just discard the old one. This is a much more graceful way of dropping packets than what we currently do. We'd likely make things quite a lot better. The other thing we can do is that we can shard the R tree by entity ID, so that instead of having two R trees like this, we have another two, and the ones with odd entity ID go here, and the ones with even entity ID go here. And that way you can have one thread updating this one and one thread updating this one at the same time. And of course that you don't have to use two, you can use a bit more. The cost is that you have to query that many R trees every time you build a packet. But the querying is really cheap. Of course, this would all have to be reevaluated if you change the data structure to the nano plan or whatever. Right there. Yep. All right. Play DB. This one's quite a lot better. And something I think very similar to this is in engineering code. There's a so I've got two things we've got to do. We've got to be able to maybe schedule an entity, which is how things get into the system, and then we need to enable the processing entity schedule for the tick. Key interface is here. So it's going to fit. It does. So this is how you do a abstract data type in C++. And this update action is what you can do for each entity. You can either pause the iteration, which means that what we're going to do is we're going to call for each update, and we're going to pass a callback in. This meant to edit. We're going to pass the callback in here. I knew I was going to do live coding. So the callback, it takes a piece of data about a player, which is mutable. It takes an immutable pointer to the entity, so the entity may not exist. And it takes this player entity data, which is the thing that we have stored about the entity last time we scheduled it. The idea is it gets called with everything that was scheduled for this tick. It's able to change this as it goes. It's not able to change the entity, and it's able to change this player entity data, which is the thing that's going to be passed back next time. Entity might not exist because it might have disappeared in the interim. So we might have scheduled it for 200 ticks in the future, and then at tick 100, the entity died, and it doesn't exist anymore. So this is why this can be null. So we pass the tick number, the state of the world, and our callback into this thing, and then it calls our callback on all the appropriate entities. And then the job of this callback is to decide, well, either I'm going to forget this entity exists, in which case it's not going to get put back into the data structure, or I'm going to schedule to look at it some number of ticks in the future. So the idea being that if it's an important thing that's close, you would schedule it for a short number of ticks, and if it's an unimportant thing that's far away, you would schedule it for a large number of ticks. So I'm going to draw a diagram. Actually, you know what I'm going to do? I'm going to steal Mark's diagram.
Some people here have never met Mark.
Sorry?
Some people here have never met Mark.
They're missing out. He draws excellent diagrams. But I don't. It's gone.
You briefly display a blue screen of death.
No, that's my broken T-Max configuration.
You don't have a tab with Slack in. You can click on the link.
Yeah, here it is. Nice.
Definitely looks like a blue screen of death.
Here we go. This is good. Is that clear? Yep. It's more or less clear. Submitted. Sorry? Yes. Of course. So these things here, and so I'm seriously stealing this diagram, but so this is the play DB, and these are all the decks. And you have one per tick, and then all the entities here. This is the play entity data of the thing that's scheduled for this tick. So when you call for each update and pass your callback, the callback gets called with the information for the entity in each one of these things. And then depending on what you return, it will schedule it into one of these buckets. So if you return 3, it will put it, if you return 0, it will put it here. If you return 3, it will put it in this one. And then once you're finished, you rotate the array, so essentially get rid of this one. Now this is tick 0. Which is, I think, quite good. Again, we use boost intrusive to index the entities by ID. So that means that even though they are kind of stored in this random order, we're able to efficiently tell whether we have an entity, which enables us to do a maybe insert. And potentially, if entities were urgent and we found out in some way, we would be able to move them into tick 0 because we do know where they are because of this indexing. Again, the entities that we're processing at a time are all next to each other, so we have good data locality there. And crucially, we only look at entities on ticks that we are scheduled to look at them. So you can't say, you can't iterate over every entity that the player knows about every tick, because that's not going to scale. You have to find some way around that, and this is one way. You just look at the things that are scheduled for this tick.
So these are just the things to look at on each tick.
Yes. So So what's interesting is that the player DB is not responsible for serializing the data. The callback is responsible for serializing the data.
Right. Okay, so within that callback, you have to choose, you have to do your serialization,
Yes.
and then your return value says when to schedule it.
That's exactly right. Yeah.
Okay, interesting.
And if you don't have to serialize it, and you can, and that player entity data is what you can use to decide about whether something has changed. So you could store the previous value that you sent there, so that you're then able to inspect of whether this has changed and needs to be sent again, or whether I can omit it.
Or whether you can produce a delta.
Or whether you can produce a delta or do some kind of compression because of the way that these values are. Yeah. Dead torpedo problem. So we were not able to adequately solve that for Etherwars 2. We could tell when entities had disappeared, and we can infer that they've died, and we can send synthetic dead messages, but we end up with clouds of ether 0-point condensate. It looked to the untrained eye as if there were ships that were just constantly exploding in the air, because the client didn't realize that they were supposed to be gone. It's tricky. The solution, which was done in Etherwars 3, I believe, was we introduced the idea of a drop message, which is where the netcode can tell the client that I'm not going to send you any more updates for this entity. So you can be much more liberal with a drop message than you can with a death message. So whenever you have a hiccup, you can send a drop message, and then the client knows not to overreact, and it can pick it up later if it reappears. So I think this works a lot better, and I think it potentially can simplify a lot of the code as well, because it gets rid of a lot of the edge cases. Yeah. Okay. Clients. So I think this is the worst job that we did.
I was actually wrong with the death messages though.
It's really complicated. It's like really complicated, and
I'm just saying from like that's quite a pessimistic slide. From a design perspective, the things look different from the slide.
sorry.
From a design perspective, death messages should have worked fine.
Well,
Things that
it's difficult. Yeah, and especially like with the issue that we had with the sometimes agents can spread it and disappear because of the way they're stored.
Yes. Okay. That.
So
yeah.
compensating for these different things made it very difficult to reason about and fix.
It's more complex to decide when to send job message than to decide when to send text message.
It is because when you send a death message, the thing explodes.
Yeah.
When you send a drop message, then the client knows, oh, we're not sure what's going on here. So now the client can simply say,
How to decide when to send the job message?
well, if you're not sure, you send a drop message.
To send job message every day.
Sorry?
Every time you send update, send a job message. Is that how good?
Absolutely not, no.
So how to decide when to send job message? What do you mean not sure?
So when the client, when the entity is not in the world database, what do you do? Well, one thing, what we were doing is, we'll just schedule it for the next tick, and we'll record that we've done that. And then after this happening 5 ticks, we will send a death message.
Yes.
Death message, yeah. Because this thing's disappeared, so it must have died. But this is like disgusting. It's much clearer to just say, well, we're not sure, so send a drop message. The other issue that this is about, I haven't really talked about, is that this is the player and this is the interest radius. When a ship moves from here to here, this is the other instance where you send a drop message. Right.
But you still do some updates for the same outside of the route.
Sorry?
Do some updates for saying outside that distance.
Sometimes, but if we had drop messages, we would just drop them. We just send a drop message
I didn't know some updates anymore.
until they come back.
Okay.
What does the client actually do with when the client receives a drop message, it knows to store the current state as it's seen it, and then whenever it needs that state, it will consult it.
Another point I just wanted to cover, I forgot to mention it before with the archery update, because it's so expensive. We have a trick where, because we're indexing these things spatially, rather than every tick moving this to where it's supposed to be, we only do it every, say, 20 ticks. So because the only thing this is used for is for the players to query for entities that are newly in their range. Now, when those are new entities that have just spawned, like a torpedo, then we'll put it straight in. But we don't update the positions of things that move very frequently. So what can happen when they query is that they're querying like a slightly out-of-date database. So the bad case is when you have something here that's moving in, and it may get updated here, and then not get updated, then get updated here. And so when it's truly here, but it hasn't updated yet, it's not going to be returned by that query, so it's not going to be sent to the client. And this is because it's really expensive to update this tree, so by doing it much less often, we can save a lot of compute. But yeah, is that clear to anyone how that works?
Yeah.
Yeah. I got three thumbs up. So this is really just about, thank you, about lag on seeing things come towards you so you're trading off some of that lag in order to have a faster update. All right, so getting back to this. So what do we do? Well, we wrote a protocol library. There's 2 functions. One's called encode packet, and one's called decode packet, and it was a brilliant innovation. Once we did this and we weren't implementing the same thing in each client, then things got a lot better. We had 2 compression schemes, so zstd and transcoding, general compression and a domain-specific bit packing scheme. It's expensive. We pass flags to encode packet on whether to do the Z or the transcoding, and it's encoded in the header of the packet. So the client doesn't have to know what to expect. It gets whatever it gets and deals with it. And these are also used for the worker to send data to the mooxer. This is what I'm thinking about when I draw that diagram of the user code talking to each other, is that they should be doing this kind of thing where they're calling the same functions and doing the same validation logic. And then by being able to dynamically zstd or transcode, we can actually do some really cool things like like just zstd every other packet, or don't zstd so much when you're under heavy CPU load, and then the client can just deal with it. But the client needed more than that. Because we had this scheme that we were iterating on to send things more or less frequently, we actually needed some higher level decoding logic in the client, so that the Unreal was just receiving essentially a hash table of every entity, every tick, even if it wasn't from the packet, so that there is some state living inside the I guess it's the rep client that is even doing maybe a bit of interpolation to fill in the data that has been omitted, because we can't send everything. So for example, we wouldn't send the type every time, but then when we decode the packet, it would fill in the type for us. If we didn't zstd or one thing we could do is not zstd or transcode to auto clients, and then get maybe 4 times as many auto clients running on a box, which is good if you care about how much it costs. Okay, what kind of results? So we ended up with about 300 kilobytes per second per client, about 1,000 players per mooxer. From what I saw, looking at one HTOP screen, we should be able to get twice as many players per mooxer. What was holding us back was the archery, and Tiago adjusted the delay so that it was a lot cheaper. So we probably could do 2,000 players per mooxer, which is what the net relevancy was doing. Will it scale? It will not. This relies on the netcode holding the entire world state into memory, and there's only so much memory. So what does this look like? So yeah, once you've got too many agents, entities, too much complicated stuff in your simulation, you're just not going to be able to hold it all in memory, so you have to partition it somehow. But you can't when a mooxer can have players, any players in it. You have to spatially partition the players, and then essentially have a mooxer or netcode cover areas of space in the same way that the ether workers do. It's like quite similar. Even though you're responsible for these ones, you need to know about the things here, so they kind of have to hand over to each other. It's not really because the workers send the data, but whatever. And then so you'd have a mooxer here. Players from all over the world would connect. Well, no, mooxers from just close to the mooxer connect. And then they go anywhere they want in the game world. So one of them goes here, one of them goes here, and then you have your ether workers over here. Exactly, everyone draws ether workers, and they just send the information to the netcoders that are covering that area of space, and then the netcoder will then send the packet back to the mooxer and out to the player. Is that clear?
So this might be a good place to have a brief interjection about the history of the mooxer.
Go on.
So when we first made ether, right, by which I mean Patrick first made ether, we had this cool tree with all these workers all doing a bit of computation.
Mm.
But we needed to, because the client wanted to see the whole world, we needed to mux all the outputs from all these different workers together so that they wouldn't be spatially partitioned for the client.
Mm.
What does that mean?
Because you did this.
Yeah.
So what you're proposing here is essentially that you have your spatially partitioned workers, which send their data through the mooxer, which muxes it all together. And then, well, or rather, no, you have your spatially partitioned workers, then send it to the spatially partitioned netcode that then sends it to the players.
Yeah.
What if instead the players just connected directly to the workers and you handed them over
Yeah,
from worker
potentially.
to worker once?
Potentially.
Because you could get rid of this whole infrastructure.
Yeah, potentially.
So,
There's probably a lot of details that I don't understand, but potentially.
like the network, like generating packets, though, is an incredibly expensive thing to do.
Yeah, so the
Just
thing is
work
that
things.
you want it to, it needs to be a pipeline system because you, like the workers, you need to be able to parallelize this work, right? And so having a pipeline system works. It maybe even makes sense for there to be a one-to-one correspondence here. I don't really know.
There is, in fact, a more interesting history here. The original reason the Mux was created is because you can't open ports, or couldn't open ports on Hazy OS. And so the workers would connect to the Muxer, and the clients would connect to the Muxer, and it was a rendezvous point.
No, it was also because there was no well-defined IP for Hagian process, right? So
Yeah, but
you had
you can't
to.
open ports.
That's the
Right?
TCP bridge.
Yeah.
So, but this still remains true in the sense that workers are quite dynamic.
Yeah.
So even if you were to have these, like the stability, or rather, even if you were to make spatially partitioned netcode, you still want something that's stable, so you're not establishing and reconnecting.
Which sounds like you
on
want
top
some
of
kind
this,
of
you might
movable channel.
want to have separate processes on top of this that will do the work for authentication and handling connections.
Yeah, well, I mean, that stuff presumably will still be here. But yeah, I think that the time of like globally aware mooxer will come to an end at some point. So we should be prepared to get that around. So I just wanted to point out that generic netcode and Ethernet netcode are pretty much parallel approaches. I think generic netcode has stolen some of the best ideas.
I'm not sure what Etherhunt is a solution for deck messages.
I made no claim. So I think we should take the best coding patterns from each of these and make them available to the Does anyone have any questions?
So once upon a time, this would have been like one of our secret sources that we deliberately didn't want to reveal to customers. It's sort of ironic now that we're basically sticking it inside a header file and sort of explaining exactly how it works.
Ah, but we might not be. So this is the point of the
might be.
netcode.
No, it's there. The SDK with comments.
So, which parts do you think are secret source?
Probably just about anything in Douglas's talk, really, about R trees and the second R tree and how we're doing querying and deciding what to send.
Okay, I'll take a look ahead of time. Because the intention is that we turn this into a netcode standard library, right? That does not necessarily mean that the standard library is open for people to inspect. It means that people can pick pieces out of it.
I would suggest it will be a lot more useful to people if it is open.
Indeed. So
It's very hard to write stuff that's like configurable in just the right way.
Yeah.
But also,
It's something that we have to consider.
it's generic, which usually means that it's parameterized on types, which makes it quite hard to make it non-generic without.
Sure, but I mean, technical details, like in terms of the direction that we want to go, it's about, yes, there are certain things, like the Ether Wars 2 netcode is an incredibly complex beast that's a significant technical achievement, right? And that it would be worth us considering how much of that we want to keep secret, because it is quite an impressive achievement. Right? I've mentioned before that I think that the design of the mooxer and the netcode and the like is probably one of the, and the ability to handle thousands of connections is one of the defining achievements that we have got to so far. So indeed, it needs some careful. Yes.
Chris.
Yeah, I think it kind of follows on to that point. You mentioned halfway through that Terry was able to tune the artery and boost performance. Is that something we expect to allow customers to be doing themselves, or are we planning on tuning the artery with
Yeah. I mean, when I say tune, I think that, I mean, essentially, it's just changing the constant for how it's the trade-off between lag and seeing things.
It's well, say different method implementation from, well, it depends what method implementation they're using. The specifics, the game's called netcode.
Yeah. I mean, in general, that is the kind of thing that they would need to be able to tune, I think. But I would hope that when we ship them this in a standard library, that it is using a more appropriate data structure that that doesn't require that. But although there will inevitably be tuning points that will be needed often.
So the part I hate about one of the design is the way you have to keep scanning your local area to see all new entities. And I was wondering what you thought, whether there's some data structure where a client can literally register an area of which it gets notifications for, and then have an efficient data structure where you only get notifications when things move in or out of your radius.
I know of no better way of doing it, and the queries are that don't show up in the blender. So I agree, it's annoying, but like there are lots of clients is the problem. So if you have some notification system, then you're going to end up firing a lot of notifications. Like you need to check a lot of times whether you need to notify. Or, I don't know. There's probably something. But yeah, but I don't think it's not a problem for now. Although perhaps it would be if we changed to a different spatial index that was slower to query in exchange for being faster.
Yeah, I think that dual netcode currently has something that's slow to query. I've not worked out why.
Yeah, maybe it needs an off tree inside the packets.
Fortunately, we have one to help.
So basically, we just need a separate instance of Ether running inside the mooxer.
Exactly.
That's one. Yeah.
I'm not bored, I'm clapping, it was a great
Well,
talk.
thanks, I appreciate it. Oh, and next week's my last week before I go on holiday to the outside of the world. So happy to answer any questions that you come up with, but
Is this developing somewhere? The documents that you showed?
yeah, it's not right on here.
Douglas is going to paste this on the Talks channel immediately.
Yeah, I'm going to
after he
paste
gets
it.
back to his desk.
Absolutely going to paste it.
Good. Thanks, him.
Do you know about all resistment?
I think you can answer that question for yourself. I started off doing reveal.js and then
Have you ever seen one of Brave?